Well friends, in the earlier module, we have discussed about vector physical quantities and their representation in different coordinate systems. We have studied mainly the polar coordinate system, cylindrical coordinate system, Cartesian coordinate system and spherical coordinate system. All these coordinate systems, they had only 3 coordinates. What if the coordinate system has more than 4 axes, 5 axes, 6 axes like that? So, if in general we are having a coordinate system having more than 3 axes, how to represent a vector quantity? Further, if the vector quantity undergoes a change in coordinate system, how to account for such a change when viewed from another coordinate system? There are many such issues whenever we consider coordinate transformation in different coordinate systems. This issue has vital importance in calculus, and that is why we are going to study it in this module. The issue is known in literature as contravariance and covariance of physical quantities. If the coordinate systems are not orthonormal, orthonormal means the axis they are perpendiculars and the unit vectors they obey the normal laws of scalar product and vector product. In such a case, we have to search for some alternate mathematical tool. So, in this module, we are going to study about such tools and techniques also. This issue finds its origin in the 19th century in the study of algebraic invariant theory and has many applications in the fields of digital signal processing, digital image processing, statistics and many others. The knowledge about this issue is quite but essential for understanding the topics like Einstein's theory of relativity, and that is why we are going to study this topic. In the literature, if you refer, this topic has been discussed with much more mathematical rigor. However, in this module, we are going to study it quite at elementary level. Objectives. In this module, you will be able to understand the concept of contravariant and covariant vectors and know about the symbols, conventions and related terminology. You will also understand analytical and graphical methods to obtain covariant and contravariant components of a given vector. In addition, you will come to know about the application areas of covariant and contravariant vectors. What we need to know for understanding this topic? We should know the terms like coordinate system, components of a vector, unit vectors, gradient, etc. We should also know how a vector can be represented in different coordinate systems using its component and unit vectors. This much background covered in the earlier modules is adequate to discuss the topic of contravariant and covariant vectors. Now, think about a vector given in one coordinate system. The vector representing a physical quantity may undergo a change with space and time. In such a case, how to represent the vector in another coordinate system without affecting its original basic features? For example, the magnitude of the vector should not change under coordinate transformation. Also, while doing so, we have to note the way in which the components of a vector are going to change due to coordinate transformation. The mode of variation of components is also important. What are such transformations meeting this and some other requirements? Actually, vectors are simply vectors. They are independent entities. They have their own magnitude and specific direction. When it comes to their representation in different coordinate systems or representations, several issues arise. Contravariance and covariance is one of such issues. Whenever we say contravariant or covariant vectors, it be noted that we are referring to the way in which their components vary in the two representations. let us discuss about some important aspects of these two types in brief. Before we discuss what is meant by contravariant and covariant vectors, let us see what we understand by the two words. When we find somebody using the phrases like controversial situation, controversy in the argument, etc., we immediately have a feeling of something happening exactly opposite to the expected one. On the other hand, words like cooperation, coordination give us a feeling of some helpful act or friendly behavior, isn't it? Is there something like this associated with the phrases contravariant and covariant vectors? Keep this point in mind and try to get the answer while studying this topic. We may think of algebraic functions to understand meaning behind these terms. As an example, consider a sinusoidal waveform y is equal to f of x is equal to a sin x. If x is incremented slightly in the forward direction, then the graph of f of x shifts in the backward direction. Any decrement in the value of x in the backward direction will shift the graph in the forward direction. Thus, we know that the shift of the graph of f of x is exactly opposite to the change in variable x. As against to this example, we can generate algebraic functions which respond in the same way as change in the variable x. Can you try on your own? Now the question is, if we have algebraic function showing such behavior, can we not find vector quantities showing such behavior? The answer is yes, definitely yes. In support of this, let us discuss about two physical quantities, namely linear velocity v and the potential gradient d phi by dx. For simplicity in understanding, let us consider the quantities in one dimension only. Have a look at the variation in the magnitude of each of the two quantities due to change in scale of the distance. Careful observation will reveal the fact that when the distance scale is reduced from meter to centimeter, the magnitude of the velocity is increased, while an increment from meter to kilometer in the distance scale causes a reduction in magnitude of velocity. Thus, the magnitude of velocity changes exactly in opposite way to the change in distance scale. We describe this fact by saying that linear velocity is a contravariant vector quantity. Now, let us have a look at the contents of the table regarding potential gradient d phi by dx. Here we observe that when the distance scale is decreased from meter to centimeter, the magnitude of the gradient also gets decreased. When the scale is increased from meter to kilometer, the magnitude of potential gradient also gets increased. Thus, the magnitude of potential gradient varies in accordance with the change in distance scale. We describe this fact by saying that potential gradient is a covariant vector quantities. Can you think of some more examples of contravariant and covariant vector quantities? Many examples of contravariant and covariant vectors can be found in literature. For example, all normal vectors such as displacement or any derivative of position vector with respect to time such as velocity, acceleration, etc. are contravariant vectors. Gradient of any scalar function is a well-known example of covariant vectors. Rather, any vector physical quantity which varies inversely with distance is a covariant vector. The term covariance and contravariance were introduced by James Joseph Sylvester in 1853 in order to study algebraic invariant theory. Several ways exist to describe contravariant and covariant physical quantities. Mathematical analogies also may help in understanding the terms in an easier manner. For example, note the following definitions. Definition 1. Under a transformation of coordinates, the physical quantity which transforms like coordinate differential is called as contravariant physical quantity. Definition 2. Under a transformation of coordinates, the physical quantity which transforms like the gradient of a scalar quantity is called as a covariant physical quantity. What is the meaning of the term coordinate differential used in definition 1? Let us refresh our knowledge about it in brief. Consider a continuous function y of multiple variables x1, x2, x3, etc. up to xn. That is, let y is equal to f of x1, x2, x3, etc. up to xn. Incremental change in the values of continuous variables x1, x2, x3, etc. up to xn will cause the net change in y, which is given by dy is equal to dabba y by dabba x1 into dx1 plus dabba y by dabba x2 into dx2 plus etc. The scalar quantity dy is called as total differential of y, while the quantity dxk is called as the differential of the coordinate xk. The partial derivative dabba y by dabba xk represents the sensitivity of y with respect to variable xk. It is also called as gradient of y with respect to xk. There are different ways in which the terms contravariant and covariant can be found to be explained by different authors. It be noted that with change of coordinate systems, the components of the vector may change. However, the magnitude and direction of the given vector do not change. Let us see another way of describing the contravariant and covariant vector. For simplicity, let us select two-dimensional representations, that is coordinate systems, namely S and S dash. Let x, y be the coordinates of a point in S and x dash, y dash be the coordinates of the same point in S dash. How x dash, y dash and x, y are related with each other? There are mathematical methods for obtaining such relations. We know that any increment in value of x and y will contribute to the value of x dash and y dash. For this, we have to account for the rate of change of x dash and y dash with respect to x and y. Taking into consideration this point, the new coordinates can be mathematically obtained as shown. This type of transformation is called as the contravariant transformation. The other way is as shown. This type of transformation is called as covariant transformation. Note that the coefficients of x and y in the contravariant and covariant transformations are reciprocals of each other. While discussing any such theory related with mathematical representation, it is always better to have a knowledge about symbols, then the method of graphical sketching, the meaning and interpretation of various terms, different concepts, and that is why we are going to study about some symbols and conventions to be followed in connection with contravariant and covariant vectors. We use coordinate systems. The Cartesian coordinate systems generally is represented by x, y, z axis and the coordinates are given by x, y, z. However, one may represent the coordinates by x1, x2, x3 also. The unit vectors are generally represented by I, j, k. However, one may select Ex, Ey, Ez also to represent the unit vectors. So, there are so many ways in which different authors they represent the coordinate systems. The other term which we use is manifold, As I mentioned in the beginning, we can have n dimensional systems, that is there will be more than 3 axes. In such a case, we use the term manifold. If it is a one dimensional representation, then we use one fold. If it is two dimensional, that is 2 axis, then it is called as a two fold. 3 axis, 3 fold. In general, if the representation or the coordinate system has n axis, then it is called as a n fold. In general, we can have manifold coordinate systems or manifold representations. So, please note this point while discussing or referring to the literature regarding contravariant and covariant vectors. The term basis in physics is used to represent a set of reference axes. The base vectors of a representation can be expressed in various ways. For example, one may use I1, I2, I3 instead of I, j, k as the basis for Cartesian coordinate system. However, generally the base vectors for other systems are represented by a letter E with suitable index I, j, k, etc. as a superscript or subscript. Base vectors need not necessarily be unit vectors in conventional sense. Let us see the conventions used to represent components of contravariant and covariant vectors. The contravariant components of a vector, say v cap, are represented with upper indices. The covariant components of vector, say v bar, are represented with lower indices. A vector v in terms of its contravariant and covariant components is written as shown. Covariant vectors are also known as one form. In linear algebra, covariant vectors are represented by row vectors, while contravariant vectors by column vectors. In quantum mechanics, the covariant vectors are associated with the notation known as bra vectors, and the contravariant vectors are associated with the Kate vectors. See the representations. The inner product of a vector with itself is expressed using contravariant and covariant vectors as shown. Note that the base vectors in contravariant and covariant forms form a pair of reciprocal vectors, while their inner product is 1. Inner product is also known as dot product or scalar product in physics. Reciprocal vectors. Two vectors A bar and B bar are said to form a pair of reciprocal vectors if their inner product is 1. The coordinate system is said to be orthogonal if the inner product of any two base vectors is 0. If in an orthogonal coordinate system, the inner product of every base vector with itself equals unity, then the coordinate system is said to be orthonormal. Curvilinear coordinate system is a coordinate system in which the coordinate axis may be curved. Well-known examples are plane polar, spherical and cylindrical coordinate systems. Generally, x, y, z or x1, x2, x3 represent Cartesian coordinate system. Any system of coordinates other than Cartesian is represented in general by using some other letter, say q. The mathematical functions relating the coordinates of a point in one coordinate system to those in another coordinate system are called as transformation relations. As an example, the transformation relations for Cartesian and cylindrical coordinate systems are as shown. In the module on coordinate systems, we have seen such relations. When we describe the same thing using two different representations, some quantities must remain invariant, that is unchanged. The transformation relations used must take care of this fact. For example, magnitude of the electric charge speed of light or temperature at a point should not change with change in coordinate system. Such quantities are known as invariants under those transformations. Inner product is an example of such an invariant quantities. It will be observed that whenever the components of a contravariant vector transforms in one way, the components of the corresponding covariant vector transforms in an inverse way in order to leave the invariant quantities associated with the vector unchanged due to transformation. Now, let us see how to obtain contravariant and covariant components of a given vector geometrically. For understanding the procedure, we will use system of two axes in a Euclidean space. Let it be required to obtain the contravariant and covariant components of the vector t in a coordinate system with axes OB and OC. Let the given vector, say t bar, be as shown. Note the coordinate system with axes OB and OC. Through O, draw a vector OP bar parallel and equal to t bar. Now, for determination of contravariant components, through P, draw lines parallel to OB and OC, meeting OB in M and OC in N. Then, OM and ON represent the contravariant components of the vector t along OB and OC respectively. To obtain covariant components, through P, draw PQ and PR perpendicular to OB and OC, meeting them in Q and R respectively. Then OQ and OR represent the covariant components of the vector t along OB and OC axis respectively. Generally, we deal with orthonormal coordinate systems such as rectangular, spherical or cylindrical. In such representations, the distinction between the two types of vectors is not so clear. However, when we deal with the general non-orthogonal curvilinear coordinate systems, the distinction becomes clear and achieves prominent importance. Let us see some important points related with such curvilinear coordinate systems. Again, for understanding purpose, let us consider a two-dimensional curvilinear coordinate system. Consider a point P in this system with q1 and q2 as the coordinates of the point P. Then q1 equal to constant will generate a curve S1. Draw tangent and normal to this curve at point P. Now consider q2 equal to constant. It will also generate another curve, say S2. Draw tangent and normal to this curve at P as shown. Thus, we have the diagram as shown. Now consider a vector PA bar equal to V bar. We know how to resolve a given vector along a specified direction. Accordingly, the vector V can be resolved by drawing perpendiculars on tangent vectors E1 and E2 to get the components V1 and V2 respectively. These components are the contravariant components of V. The vector V in terms of its contravariant components can be represented as shown. The vector V can be resolved along the normals to get the components V1 and V2 respectively. These components are the covariant components of V. The vector V in terms of its covariant components can be represented as shown. Compare the two representations of the same vector V. In brief, it be remembered that the contravariant components of a vector are obtained by projecting on the coordinate axis, that is along tangents, while the covariant components of a vector are obtained by projecting on the normal lines to the coordinate hyperplanes. Theory is better understood with the help of numerical exercises. So, let us have a small numerical exercise to understand how to obtain the contravariant and covariant components of a given vector in normal orthogonal representations. Please note the steps and design your own problems on similar lines. The problem reads like this: given a vector a bar is equal to 3i plus 2j, obtain its contravariant and covariant components in the basis E1, E2, E3, where E1 is equal to 4i plus j, E2 is equal to 2i plus 3j, and E3 is equal to k, wherein I, j, k are the unit vectors in Cartesian representation. Note that the given basis forms orthogonal coordinate system. This is because the dot product of at least one pair of two different base vectors is non-zero. It is an easy job to obtain the covariant components of a given vector. They can be obtained simply by evaluating the dot product of the vector with base vectors as shown. However, the determination of contravariant components and the corresponding base vectors needs some numerical computations. Try to understand the steps used in solution for this purpose. We need to evaluate the scalar triple product of the given base vectors, which is to be used further in computation of the contravariant base vectors. Note the order of cyclic shift of rows in the vertical direction in the determinant used while computing the base vectors EI. Thus, knowing the contravariant base vectors E1, E2, E3, we are in a position to compute the contravariant components of the given vector. These components can be obtained by evaluating the scalar product of the vector A with the contravariant base vectors as shown. Thus, finally, we have the solution as shown. Using the computed values, we can verify the fact that the vectors represented using contravariant and covariant forms match with the given vector as shown. Also, we can verify that the contravariant and covariant base vectors pairwise form the system of reciprocal vectors. This can be confirmed by showing that the dot product or inner product of respective pair of base vectors in the two representations equals unity. Can you try to plot all the vectors involved in the solution on a graph paper? XY plane can be a good choice for the same. Verify your answer with the one shown here. Raising and lowering operators, namely G, Ij and Gij with indices Ij used as subscripts or superscripts can be used for interconversion of components of covariant and contravariant vectors. For example, if we know covariant components Ai of a vector A, we can obtain its contravariant components A superscript I using the relation as shown. This is called raising the index. For a given value of index I, we can compute A superscript I by taking k equal to 1, 2, 3 in matrix form as shown. Similarly, if we know the contravariant components A superscript I, we can compute its covariant ones by using the relation as shown. This is called lowering the index. These two operators are inverses of each other. Let us see some examples to understand the computational aspect of lowering and raising operators. As a first step of the solution, using the covariant basis vectors, we can compute the lowering operators as shown. Similarly, if we know the contravariant components A superscript I, we can compute its covariant ones by using the relation as shown. This is called lowering the index. These two operators are inverses of each other. Try to understand the computations involved in the application of raising and lowering of operators as shown. The solution is as shown. Find the contravariant components of vector A, knowing the lowering operator and covariant components of vector A bar. The first step in the solution is to find the raising operator, which is the inverse of the lowering operator. Given covariant components A1 is equal to 43, A2 is equal to 34, A3 equal to 0. Using the lowering operator, the contravariant components can be computed as shown. For a given coordinate system, expressions for Gij can be derived in many ways. Use of coordinate transformation relations is one of the methods. For example, in polar coordinates, that is in 2 dimensions, polar coordinates of a point are given by r theta when the relations are x is equal to r cos theta and y is equal to r sin theta. Using these relations, the lowering operators can be obtained as shown. The raising operator is obtained by taking inverse of the lowering operator and is finally as shown. Well friends, so far we have discussed about some elementary and technical aspects about contravariant and covariant vectors in a superficial manner. In reality, it has a very wide scope and practically finds no bounds. At the end, we will discuss about one miscellaneous point and application areas of the concepts of contravariance and covariance. Whenever the question of coordinate transformation comes, we get reminded of Einstein's theory of relativity. Einstein's theory of relativity involves the description of an event by two observers which are in relative motion with respect to each other. Let us see what is meant by the term an event. Number 75. Loosely speaking, an event in relativity is characterized by specification of location, that is, position coordinate of the place of occurrence of an incidence and the time instant of occurrence of the incidence. Thus, the entity event has 4 coordinates, 3 space coordinates and 1 time coordinate. They are taken together to represent an event. We describe this aspect using the phrase space-time continuum. Lorentz transformations relate the coordinates x, y, z, t of an event as recorded by one observer to the set of coordinates x dash, y dash, z dash, t dash of the same event as recorded by another observer moving with constant velocity with respect to the first observer. The description of the same event with respect to space and time can be different by the two observers. The relations are as shown. Thus, since the description of any phenomena depends upon the velocity of the observer, it becomes quite but essential to reformulate the laws of electrodynamics, especially the Maxwell's equations and Lorentz force, in such a way that they are invariant under Lorentz transformations. Concept of covariant formulation of electrodynamics becomes of prime importance in this regards. The concept of contravariance can be found to be used in object-oriented programs, vector spaces, differential geometry, image processing, category theory, and many other fields. The concept of covariant derivative of a contravariant vector quantity finds many applications in physics and biotechnological applications such as analysis of neuroimaging data centered to the cortical surface of the brain. Well friends, so far you have coined the terms like scalars, vectors, pseudoscalars, pseudovectors, and now contravariant and covariant vectors. Definitely you will ask the question, what is the topic a step ahead of contravariant and covariant vectors? To get the answer, may I request you to think over one question. The question is like this: how to analyze the situation wherein the components of a vector themselves behave like a vector. Just think and you will get a clue about what to study further. Thus, to summarize, we may say that the quantities which vary like coordinate transformations are contravariant, while those which vary as gradients are called as covariant vectors. We can have interconversion of covariant and contravariant vector quantities by using raising and lowering indices. The contravariant components of a vector can be obtained by projecting the vector on the coordinate axis, while the components of covariant vectors can be obtained by projecting the vector on the normals. The concept of covariant and contravariant vectors finds many applications in the field of image processing, computer programming, statistics and many others. Thank you.